was building up tools to deal with these ideas, which is where I kind of really wanted to get to. We definitely don't have enough time to get to where I really want to get to, which is supersymmetric quantum mechanics. But well, let's see how far we can go. So this might sound like a bit of a contradiction in terms, and the reason I say this is because topology is the study of global properties of things, whereas calculus, and essentially things differential, is really a study of local properties of things. So when you did calculus for the first time, you were interested in taking a derivative, and taking a derivative meant comparing a function at some point to the value of that function at some nearby point, and then making those points even closer and closer together. This led to the idea of differential calculus. Right? The differential calculus derivative differential equations are all about local properties of functions. Topology, on the other hand, has a bunch of integrals associated to various quantities of digits. Okay. Integrals are global things. Topology is the study of the consequences of continuity on spaces. Okay. So differential topology sounds like a bit of a contradiction. But actually, it's not. It's using the ideas that we've been building in the last 22 lectures about doing calculus on manifolds to say things about global structures of these spaces. So that's what we want to do in set of lectures. Okay. So essentially, I want to break this up into a couple of different things, and hopefully I can at least get to radiology by the end of the course. But I want to start off by revisiting vector calculus and trying to frame some of these questions in the language that you're most familiar with, the language of kind of advanced calculus. Right? And then we'll, of course, generalize this and try to use some general formulae for calculating things. And then I want to frame things in terms of homology and cohomology spaces. These vector spaces become groups if we restrict our attention to the field of integers. And we'll talk about this. And I want to give you some very simple calculations for homology and cohomology groups, and then we'll make some grandiose claims based on those very simple observations, and that will lead us on to the idea of operating. So that's where we're going in the next 7 or so lectures. Okay, so as I said, topology is really the study of the consequences of continuity. But before exploring what I mean by this, I want to start off by making some very simple observations which you could have already made in first year. So one of the things that you would have learned in first year is that if I have some continuous function defined on some let's say I have a real value function defined on some connected interval. Okay, so some segment of the real line. I have a function that's a real value continuous function on this defined on this interval. And if this function is negative at some point and positive at some other point, then it has to have gone through 0 at some point. Okay, this is something that you would have learned in first year. Okay, so one consequence of this statement is the fact that if I have a continuous function and it's defined on a unit circle, then it must have 2 diametrically opposite points at which the function takes the same value. Let me prove that. So we'll start off by recalling that a continuous function define continuous real value function defined on a connected interval. Continuous function f R. At some point and positive some other must vanish somewhere in latitude. Good. So one consequence of this is that if f is defined on a circle, if f has circle R, unit circle R, then there must be some value of theta, let's say theta star, such that f of theta star plus pi is the same as f theta star. In other words, there are two diametrically opposite points at which f takes the same value. Okay. This has real life consequences. Let me show you one. In fact, I'm going to leave it as an exercise, but I'll prove this statement and then I'll state the thing that I want you to show. All right. So see this. Let's define capital F of theta, the little f of theta plus 2 pi, little f of theta plus pi minus f of theta. So if f of theta is 0, then we're done. Okay. But let's say that f of theta is not 0 and ask what is f of capital F of theta plus 2 pi? Sorry, capital F of theta plus pi. Capital F of theta plus pi is f of theta plus 2 pi minus f of theta plus pi. But f defined on a circle, assuming that it's single valued on the circle, which means that f of theta plus 2 pi f theta. So this is equal to f theta minus f of theta plus pi with minus capital F of theta. right? I'm also assuming that this guy is continuous on the circle, which means then that this guy is continuous on the circle. So now I have a continuous real value function that changes sign. So it's got to go through 0 at some point, which proves this statement. So here's the real life application of this story. Coffee shops. I bet you didn't think I was going to stop the sentence like that. Sorry, can I just coffee shops typically have four-legged round tables, especially if they're crowded. Right? So if you go to a coffee shop and you see a four-legged round table, and let's assume that it's not one of these progressive coffee shops where you have these dialable legs. So all the legs are equal length. Okay? So they don't give you the option to change the length of the table as you wish. So you have a round table with four equal length legs. Okay? If your coffee shop is anything like this room, then you'll know that generally speaking, the table will be wobbly because the floor is uneven. Okay? So here's my exercise for you. Using this argument, using this statement that we just made, I would like you to show that rotating the table to an angle less than pi by 2, you can find a stable point for the table that has one. Using this argument, show that a wobbly four-legged round table may be rotated to an angle less than pi by 2. I don't know what that angle is, it's not a unique angle, but it's going to be less than pi by 2. To a stable configuration. By stable configuration, I mean that all four legs, equal legs are touching the floor. And by wobbly solution, I mean 2 legs are touching the floor and 2 legs are not touching the floor, and then wobbles. Yes, sir.
I mean, like the unrealistic assumption that the floor is continuous.
That's like the problem. How do you see this? So yes, there's no steps along the way. Yeah, depending on the concept, that might be realistic or not. Okay, great. So right. Much of the development of this field and differential geometry actually came from applying these ideas to physics problem. And much of physics takes place in vector spaces, typically on curved manifolds. And when you're studying vectors on curved manifolds, one important question you might want to ask is whether these vector fields are well defined globally, whether they're well defined in the entire space. Okay. This is not a trivial consideration by any means. And in fact, a lot of really important results in physics, mathematical physics, arise from the fact that some of these things have obstructions. So, for example, and to illustrate, a smooth vector field defined on the two-sphere S sphere. You can convince yourself by drawing arrows in the sphere, that such a smooth vector field defined on the two sphere must have somewhere where the vector field is zero. Okay, in the physics of black holes, this is the statement that black holes don't have hair. In other words, if you think of a vector field, black hole physics would call hair on the black hole. There's no way that you can comb that hair on the black hole in such a way that it doesn't look like it originates from somewhere. That's the zero of the vector. This is the topological statement. This is a statement that vector fields, smooth vector fields defined on the two sphere have to vanish somewhere. Okay. The same is not true if you consider smooth vector field defined on a torus, two torus, for example. Okay, there you can have a hairy torus. Okay, where the hair doesn't look like it originates. The fact that if you try to do this on a two sphere, you will always end up somewhere where the vector field vanishes, is actually why you can't have such vector fields defined on the surface of a black hole. Is because you take an object that's rotationally symmetric. So however which way you rotate it, you shouldn't be able to tell that there's any difference. And now I tell you that there's some point that's special on this two sphere, and that's where the vector field is zero. Right? So you either have rotational symmetry or you have a vector field. So this has important consequences for example, the study of radiation on black holes. It has important consequences for the study of gravitational radiation from black holes, and it all comes down to the topological statement. Okay. So that's the first point I want. The second point I want to make is that if we want to characterize the global structure of manifolds, okay, I need some set of objects to study. These set of objects should not depend on local things that I can do to these manifolds. I want to study the global structure of the manifold. So if I take some manifold and I deform it or stretch it or I compress it or pinch it or something, it should change the global structure. So whatever quantity I am with, whatever quantity I'm working with should be an invariant. It should be a topological invariant. So what we're going to be doing in the next couple of lectures is defining a bunch of these topological invariants. In fact, we're going to be studying one set of such invariants are homology invariants, like the Betti number. So we're going to define the Betti number as related to homology spaces. I've defined the homology space as a quotient of the set of boundaries modulo, the set of cycles modulo boundaries before. The Betti number, a topological invariant, is the dimension of that space. Okay, so we're going to go through and define all these properly in what follows, and see how they are related to the global classification of space, global characterization of these spaces. In particular, what we're going to find is that any two manifolds with different Betti numbers are topologically distinct. But the converse is not true. So I can have topologically distinct manifolds with the same Betti. Okay, how that works is what we're going to be talking about. But all of this stuff together is what constitutes the field of differential topology. Okay, the use of local quantities to say things about global properties of space. And just going back to the Betti number story, if I say that the Betti number, this thing that I'm claiming is a topological invariant, which characterizes the overall topology, the overall global properties of the space, is the dimension of the homology space. The homology space I got by studying cycles and boundaries, and I defined cycles and boundaries with respect to exterior derivatives. Oh, sorry, I define cycles and boundaries with respect to the boundary operator, which is a local operator. Okay, so this is using local information to get global information about space. Okay, very good. So again, let me say, let's take a step back and go back to something that we're already familiar with in this vector calculus. So, by way of motivation, then, in your course of elementary vector calculus, we learned that the divergence of a curve was 0. And the curve of a gradient was 0. Essentially, this is because curves look like this, so they don't diverge, they don't go anywhere. And gradients look like this. They don't curve, they don't the first paper. Right. So this is the mathematical statement of this picture, and this is the mathematical statement of this picture. Okay. So the question then becomes, if I give you a vector, some vector, let's call it, I don't know, W, and I told you the divergence of W is 0. The question is, when can you write that W as the curl of some V? Similarly, if I told you that I gave you some vector, let's say psi, and I said that the curl of this vector vanishes. Question is, when can I write this vector as a vector? Okay. Now, you may or may not have heard already in second year that there's an explicit formula for this W in terms of, sorry, there's an explicit formula for this psi in terms of phi. Okay. But you probably haven't heard of an equivalent formula for a W in terms of a V. So I'm going to remind you what the phi must be in this case, and we'll write down a general result, okay, using the language reforms for this case, and then we'll check that general result. But before I do this, I need to make two statements. Essentially, I'm trying to understand when two manifolds are the same. Now, I should tell you then what I mean by the same. Okay. In this sense, let's define two things. So when we define manifolds by taking topological spaces and giving them additional structure. Okay. Same way, I'm going to define when two spaces are the same. I'm going to distinguish between two topological spaces and two manifolds. And the manifold is going to be the more restricted case from topological space. The two topological spaces are considered the same if they are homeomorphic. That is to say, I can find some one-to-one, onto, and continuous map between them, such that the inverse of that map is also continuous. Okay. Similarly, two manifolds are considered the same if they are diffeomorphic. That is to say, there's a one-to-one, I can find some one-to-one onto a smooth. So see infinity map between the two of them, whose inverse is also smooth. Okay, so two manifolds are same if they are diffeomorphic. So same story as up there, except you replace continuous screen. So the reason I want to the reason why I want to get eventually to supersymmetric quantum mechanics, believe it or not, it was one of the places where one rather substantial, I'm just going to get the number is correct. A rather substantial developments were made in differential topology. And one such was the fact that where is this? So one such fact was that there are 992 different 11 spheres. They're all homeomorphic to the 11th sphere, canonical 11th sphere, but they're diffeomorphically distinct. And this was the result that was proved by David Whitney, essentially constructing supersymmetric quantum mechanics, which I will try very hard to get to, but I don't promise anything. Okay, so having done that, let's take a step back and ask, again about this statement here. So by now, I shouldn't have to convince you that both of these statements, the divergence of the curl vanishing and the curl gradient vanishing, are both consequences of the statement that the exterior derivative is a two nilpotent operator. Okay, so the exterior derivative is a nilpotent operator. What I didn't mention the last time is that this goes by the name of Poincaré's lemma. So both of these statements are a consequence of Poincaré's lemma, just depending on what you're acting with, what you're acting on with the exterior derivative. So what we're trying to do in this story here is work out the converse of Poincaré's lemma. Poincaré's lemma says that if I take any form that's written like this, and I act with D, then because D squared is 0, D of that form is 0. But if I give you some form alpha, and I know that D alpha is 0, when can I write alpha as D of something? Okay, so that's what we're trying to do. And find the inverse of Poincaré, the converse of Poincaré. So let's take this result here and just remind you if phi of x is defined to be the integral from sin x naught to x of b dot dx, so that's the line integral. Okay, so in our case, okay. So if we restrict our attention to R3 and I define phi of x to be the line integral, sorry, it's not quite. If I define phi of x to be the integral, the line integral from x naught to x, some point x and f in R3 of b dot dx, then my claim is that the gradient of this guy is v. So what I know is that if I compute the gradient of phi, then this is the gradient of this integral b dot dx. You should convince yourself by differentiating on an integral that this is the integral of the derivative, is just b. Moreover, if I take the curl of that b, I'll get 0. In other words, here I have some vector field v, and I know that the curl of that vector field is 0, and I also know explicitly how to write v in terms of some potential phi. Okay, so this you should have seen already in a second. This is a less trivial example to work out. But instead of working on that particular example with divergence of the curl vanishes, and I'm asking what is the divergence of some vector vanishes, and then we have to ask what is the can this something be written as a curl of another vector? I'm going to work it out in general. I'll give you a general formula for how to express the potential. The thing whose derivative is the thing that we're interested in. Okay. So the question is, when So suppose d of omega is equal to 0. So I have some R form, say, whose exterior derivative vanishes. And I want to ask, when can we find a 1 degree lower form I such that omega can be written as d pi. Okay. When I can find such a form, I will call this pi a potential. The terminology deriving from electromagnetism, where the electric field and the magnetic field are the things that satisfy equations like this. And if they satisfy something like this, then I can find an electric or magnetic vector potential or scalar potential such that this is true. Okay. So we'll call the chi such that omega is d chi, we'll call it the potential. The question is, given some form whose exterior derivative vanishes, how do I construct? When can I construct the potential, the associated potential? Okay. It turns out that the when depends on the space itself. And I can do this, I can always do this, if the space is what we call retractable. Let me define that. So suppose I've got some manifold M that omega the submanifold of M on which form omega, little omega, is well defined. Then this capital omega submanifold is called retractable, the point O. If we can find a one parameter family of maps by T that takes omega, the one parameter being T, with T varying from 0 to 1. I'll do this. And phi 1 of x being x for x in omega, and phi 2, sorry, phi naught of x being the origin. Sorry, being all itself. If we can find such a map, and this is called a retraction map, And if I can find a retraction map and the manifold is retractable, then I can always find. Sorry, okay. Then if you get explicit construction, yeah.
Does the retraction map have to be continuous with also?
The retraction map has to be continuous. Okay.
With respect to T and elements in omega.
Actually, no, it has to be smooth. Yeah. And that's important in our construction. Okay. So if I apply the pullback retraction map to omega, remembering how the pullback acts. This means that phi star, phi 1 star on omega is just omega, it's the identity. And phi naught pullback on omega is 0. Okay. So now let's define the what physicists we call the velocity field associated with the plot of x mu. We call it eta mu, and eta mu is going to be dx mu by dt, the same parameter. Where x mu is flow under phi, so it's phi t on x. Using the same notation that we did when we were studying lead derivatives. Okay. Then the following is true. If I take the derivative with respect to the parameter of phi t star of omega, well, this is just the lead derivative with respect to the vector field eta of this phi t star of omega. Again, so this is all the stuff that we did when we were talking about these. So go back to your notes on that section. And then I know that I can express the lead derivative in terms of this, what we were calling at the time infinitesimal homotopy relation, which is basically just that the lead derivative is d acting on the contraction with respect to the vector field eta plus phi eta interior product with respect to eta, that's d on phi t star omega. Okay. This is the decimal homotopy relation. Derived. But we know that we know two things. One is that omega is closed, and two is that the pullback operation commutes with the exterior derivative. These two facts together tell me that I eta d on phi t star of omega is I eta phi t star d omega, that's 0. So the second term contributes nothing. And d by dt of phi t star omega is then d I eta of phi t star omega. So now let's integrate this from 0 to 1 with respect to t. Integral from 0 to 1 of d by dt of phi t star omega dt is the integral from 0 to 1 d I eta phi t star omega dt. On the left hand side is the integral of the total derivative. That's just phi 1 star omega minus phi naught star omega. If we go back to our relation here, this is just omega. This short form. And on the right hand side, the exterior derivative commutes with the integral. So I can take it out of the integral. This is just d of the integral from 0 to 1 of the interior product with respect to eta phi star of t and omega dt. Again, this is d of something. So what we've shown is that omega on a contractible space can be written as d of some potential, and we've also given a construction for what that potential must be. So if the space is contractible, then the potential is nothing but the integral from 0 to 1 of the interior product with respect to the velocity vector field phi t star omega dt. And you can see how in trying to find converse of operator lemma, we've actually implicitly utilized all of the tools that we've been building so far. There's the lead derivative, there's the interior product, there's the velocity vector field associated with coordinate flow, and there's differential forms. So this guy, chi, is a 1 degree lower form than omega. Given an omega whose exterior derivative vanishes, this is what the associated potential chi is. And the constraint on this construction came from the fact that I required omega to be a refractable manifold. Okay. Now, what I'll show you in the next lecture is that there's a practical blockage to this. So I can tell you when it doesn't happen as well. And in fact, there's a particular number that you calculate associated with omega that provides an obstruction for when you can't use. Okay. So I'm going to stop here. And we'll pick it up on Friday.